Hello. Can you guys hear me? Perfect. Wonderful. Thank you. Thank you. So we're still gonna wait a couple minutes before we start, just so any potentially late people can join us. So maybe just before we start, let me introduce myself. My name is Jakub Galecki, or in English you can pronounce that Jacob. I am a software engineer here at QuickerSim. And this webinar is going to be about the compressible solver that we offer in our toolbox. So today during the webinar, I will show one example of just a simple solution for a two-dimensional flow problem. And then I'm going to show you how to also use mesh adaptation. So once again, I'm not going to start yet, just to give everyone a chance to join. And actually, sorry, that's just a PDF I'll be using. So actually, this is kind of exciting because I don't know if everyone knows, but 2 days ago we released the new version of our toolbox, version 2.3. We were very excited. We have some really cool new features. We have some new turbulence models, I believe. We have radiative heat transfer, which is a completely new thing. We did not have, you could not model radiation previously in our software. We also have numerous bug fixes and performance improvements, including actually we have a new iterative solver, algebraic multigrid based, so it is very efficient. And essentially now, using our toolbox, you can compute fairly complex flows. Even on your laptop, the RAM limitations now are significantly smaller. Excuse me. All right, I think we've given everyone enough time. So once again, hello everyone. My name is Jacob, and today I'll be talking about the compressible flow solver. Right off the bat, let me state that I'm sorry, my voice is a little off. I'm a bit sick, so if you see me sneezing or blowing my nose, I apologize for that. Unfortunately, there's not really much I can do. So let's get started. All right. So this is just a tutorial from our toolbox that is available for you to view and download. But what I want to draw your attention to here is the equations, the Euler equations that are solved in the compressible toolbox. So this is an inviscid solver. So there will be the viscosity is equal to 0 essentially, meaning that there's obviously no turbulence because there needs to be viscosity for us to even consider turbulence. So here, this is the momentum equation. For everyone familiar with fluid mechanics, this is basically the Navier-Stokes equation, except with the viscosity term removed. Right, there's no viscosity times the Laplacian of the velocity. This is fairly straightforward stuff. The second equation is the continuity equation, or the mass conservation equation. Simply here we have that the divergence of density times velocity is 0. Once again, this is some fairly basic stuff. Anyone who has studied fluid mechanics knows what's up. And these equations are supplemented by the energy equation. So yeah, I think this is also very fairly elementary. So let's get. So I have a question right here. Can you please share the document? You can download this with our toolbox. This is included in the basic tutorial package. The tutorials are also available on our website. Also, just for anyone wondering, this tutorial will also be available on our website after we're done. So real quick, when you go on our website, basically here you have the tutorial center, and you can simply browse the tutorials here. Most of what I'm going to be talking about is available on the second page here, number 25 and 26. So basically, what I'm going to be covering today is tutorials number 25 and 26, except perhaps I'm going to be going maybe a little bit more in depth. All right, so let's get started before everyone gets bored. All right, wonderful. So we're done with the equations. All right, so the first case, 1 second. Let me just undock this and fit it into your screens. Wonderful. Perfect. Can everybody see the font? Is the font all right, or do I need to make the font larger? All right. Great. So let's run through this step by step. So first of all, we're just going to clear the workspace, and then we're going to read the mesh. So right here, view case is a new utility in our toolbox available from our new release. Basically, if you have experience working with our software in the past, sometimes it was a little cumbersome. When you imported meshes from Gmesh, you maybe didn't always remember sort of which boundary was which, and you had to go back and double check. So that is no longer the case. What happens is, after it's perfect. Oh, sorry. All right. So basically, now using view case, you can visualize your domain. And here we can see that this boundary has the ID 2. The bottom and top boundaries have the ID 3, and this one has the ID 4. So just a little about the case. This is going to be supersonic flow over a bump. So on the left, this is going to be the inlet. The inlet Mach number is going to be 1.65, I think. This is just a wall, and this is the outlet, as I said before. So let's continue. This is precisely what I just said. We're going to define sort of which ID corresponds to which boundary. Once again, you can see this here. Here we define the reference values for gas. We're going to be using the reference values for air, as is standard in aerodynamics. I mean, as everyone can see, I'm sure this is kind of a simplified, or this is a sort of a similar geometry to an airfoil. Obviously, this is a circular bump, so it's obviously not an airfoil, but it's kind of the same idea. So this is basically these sort of cases have use in aerodynamics. I'm sure everyone knows that. Wonderful. So these are the reference values, the specific heat ratio, density, pressure, gas constant, etc. So let's run those. Next, we initialize our solution, or we define the initial values. So first, we have the velocity, the horizontal velocity, the x velocity, the vertical velocity, the pressure, and the initial density. So let's run those. All right. Oh, sorry. That was a long button. My bad. Sorry, everyone. All right, let's start again. My mistake. All right, perfect. So here we're going to initialize our solution. Basically, this is a little bit different, sort of what's under here than in the case of the regular incompressible solver. because in the case of the incompressible solver, basically what you're doing is based on the initial values that you provide, you just sort of just generate the initial velocity, pressure, etc., or just velocity and pressure in the case of the incompressible solver. Here it's a little bit different because not only do we need to generate those vectors, which is obviously straightforward, but right off the bat, what we need to do is make sure that the values for the velocity that we generate, that they do not have a normal component to the boundary. So that basically we enforce a non-penetration condition right off the bat. Actually, let's just run this right now and let's visualize our initial solution. So as you can see, we just use just a horizontal vector. So we only have x velocity. But when I visualize the field, the velocity field, or the Mach number field, my bad. Yes, perfect. So here you can see that it's a little bit disturbed here on the boundary. This is, as I said, in the nodes that lie on this bottom boundary, we have already enforced the non-penetration boundary condition. And the reason that we do that initially and not at some later point with imposing the boundary conditions is that, as you can see here, I'm going to talk about this bit in a second, but in this solver, we do not solve directly for our unknown values, but rather we solve for the increment of our unknown values. This is just a quirk of the solver. There isn't, it's not critical. Basically, the reasoning behind this is if you solve for the increment in the specific finite element volume formulation that we use here, the matrices, the stiffness matrices that you get have a lower conditioning number, so they're simply faster to solve, especially when using iterative solvers. But we'll talk about that in a second. So after we've initialized our solution, we define our residual values and our number of iterations. Here, what we do here, basically, we could just choose an arbitrary value for our time increment. What current number does is it computes the time step so that it computes the time step based on the velocity that we computed here, so that the current number in, I believe, the smallest or the largest element of the mesh would make sense. Yeah, and the largest element of the mesh, of course, is, oh, no, sorry, of course, it's the smallest element of the mesh. So the current number in the smallest element of the mesh is 5. If you're unfamiliar with what the current number is, I don't really want to waste a lot of time talking about it, but you can Google the current Friedrichs-Levy condition, or the CFL condition. It's basically just a numerical condition for the stability of explicit solvers. Essentially, the whole idea is that the information in a single time step should not travel too far. So if the information in a single time step, information here meaning velocity, travels over one element in a time step, then you can then the current number is 1. Sorry, I got a little off track there. All right, I think we have some questions. So what's the scheme used for solving the hyperbolic part? I think maybe I should answer. You know what? I'll just answer this now. But basically, guys, if you could save your answers until the end, then we're going to do a Q&A. So basically, the solver that is used here, it is based on the least squares finite element method. There's plenty of literature available. If you'd like, you can also contact me directly. I studied this method fairly extensively in school, so I know a little bit about it. But the scheme used, it's a pseudo-transient scheme. So essentially, what we're going to be doing is time stepping until we achieve the converged solution. So it's neither really a steady state solution nor a truly transient one, because I mean, we can go back to the equations. So it would be a steady state solution, obviously, if we just took out the time derivative part. But then you get a whole lot of essentially convergence issues, and the scheme is unstable. And there are a lot of numerical challenges which are connected to calculating steady state solutions. Maybe somewhat counterintuitively, it's easier to simply compute a transient solution. So essentially what we're going to do is we're going to be stepping in pseudo time, essentially, meaning we're going to be calculating a not all that accurate transient solution until the simulation converges to a steady state. So until the change in the simulation from iteration to iteration is fairly small. All right, I hope that made sense. Once again, if you guys if you need any more explanation, please save your questions until the end, and I hope I can answer everything then. So let's get back to business. Yeah, so this is here we simply compute the time step, and here we get down to the interesting, or the main part of the solver. So we assemble our Euler problem, our stiffness matrix here K, and our source term vector F. This is based on the mesh, on the solution that we computed previously, and the reference values, or the specific heat ratios, and the time step, obviously. So maybe not obviously. In our incompressible solver, what we do is we simply we assemble these matrices regardless of the time step, and then we add basically we add the mass matrix, or introduce unsteady terms based on the mass matrix. Here we simply compute the matrix as in the unsteady form initially. So it's just shorter and more convenient this way, especially since we do not have a truly steady state solver. So then we're going to impose the first boundary condition on the inlet. So if we go back here on the left, there's an inlet. Far field means that we're going to define all the parameters, or all the values for this boundary. So we're going to prescribe the density, the velocities, and the pressure. I'm getting a question. Does your code can your code be used to solve explosion deflagration vessel venting through pipe? Frankly, I'm not familiar with that particular case. But yeah, my bot can answer, or my colleague, I mean, of course, who is in the chat, he can answer questions maybe to some extent there. Maybe I'll talk about it later in the Q&A. All right, so let's get back here. The next boundary condition is the compressible outlet. So basically, what compressible outlet does is that for anyone familiar, or frankly for anyone familiar with CFD, obviously if the flow is hypersonic, then the information cannot propagate backwards. Essentially, the equations are hyperbolic. So when the basically compressible outlet detects whether the velocity on the outlet is hypersonic or subsonic, and then depending on that, it either prescribes the pressure or it doesn't. It's just kind of like a smart way to prescribe the outlet pressure if you're not sure whether or not the flow is hypersonic or subsonic. And, in some transonic cases, maybe part of the outlet is part of the outlet is subsonic and part of the outlet is hypersonic. So it comes in handy here. Frankly, in this case, obviously, we know that the entire outlet is going to be hypersonic, so we don't need to call this line of code, but it's perhaps more elegant, and it's a good practice to call it anyway. And finally, we prescribed a non-penetration boundary condition on the walls. So here on the entire top boundary and at the bottom boundary, this is a bump and a channel. So the way this works, this is kind of maybe a little bit different than the standard solver. Basically, for this boundary condition to be imposed, we need to calculate a rotation matrix for the mesh, and this is I don't want to say it's very computationally expensive, but it takes a little bit of time, and since we only need to do this once for the entire simulation, since the mesh does not change, then basically what happens is that if we go here, open this, we have a persistent variable. This is the matrix that I was talking about. This is or for anyone who programs in MATLAB, persistent variables persist between calls to a function. They're a little bit like static variables in objective programming in like C++ for any programmers out there. What I'm getting at is that calling this particular variant of imposed CFD boundary condition will create a variable which will persist in memory. So if we want to compute a different case and we change the mesh, then we need to clear this function simply by calling clear imposed CFD boundary condition 2D, or by calling clear all as I did here in the beginning. This is another reason why I call clear all at the beginning. MATLAB gives us a warning, but yeah, in this case it is necessary. All right, so here we simply, as I said before, we calculate the increment of the solution. And actually, I'm going to run this now, so I can maybe talk about this while it's computing, because this will take a while. Excuse me. I apologize once again. I'm a little sick. All right. Wonderful. So here, what we will see is, as I said, this is a pseudo-transient scheme. So we will see the shock wave on the bump developing. So while this is happening, actually, let me drag this away for a second and go back to the code. Excuse me. All right, perfect. So further down, we just compute the residuals, so we know how converger simulation is. And then this part is very similar to our incompressible solver. Here we simply plot the results. So display solution 2D is one of the most commonly used functions in our toolbox. It simply displays the solution. What's unique to the compressible solver is that we have a compressible solution function. This is sort of to get around the indices structure, which is used in our incompressible solver. This is just it's a shorthand for extracting the specific values or the specific fields from the unknown vector. So you can here we have the pressure and Mach number. You can also have you can also get information about obviously density, velocity, the x and y velocity itself, and the temperature. Well, it's computing right now, so we can't open the help on this. It'll open after we're done calculating, but basically it's all in the help for this function. It's very simple. I think one of the advantages of using MATLAB and performing CFD simulations in our toolbox is that unlike some other environments, it's all very high level. It's high level programming, meaning you don't really need to write a lot of code yourself, and essentially you've done everything for you. There's a lot of help available. So it's easy to sort of get your bearings around around any issues that you may encounter. So this is still calculating. You can see the residuals here. Excuse my voice. I'm really sorry. I apologize. I did not intend to get sick for this webinar, obviously. So yeah, this is going to take a little while. I prepared this case on a fairly decent desktop computer, and it computed very quickly, or fairly quickly in like a minute. Right now I'm using a pretty old laptop, so it's perhaps not converging as fast as I would like it to. Actually, I think the results are actually available in this tutorial. Hopefully, yeah, perfect. This is a small image, but that's basically what it's going to look like at the end. There's going to be a shockwave that develops here, and here behind the bump, the shockwave is going to reflect off the wall, and yeah, it's compressible flow 101. Nothing out of the ordinary. This is just a showcase, so maybe it's not the most spectacular solution. I was hoping it would calculate faster. You can already see the shockwaves forming and the reflected shockwave over here forming. I'm gonna kill this simulation in a minute just so you guys don't have to sort of wait around. All right. Yeah, I think it's pretty straightforward and pretty clear what's happening here. All right, wonderful. So I'm gonna kill the simulation now. Yep, these are some MATLAB errors. Doesn't matter. All right. So this is, as I said, this compressible solution. So here you can get the pressure, the density, the velocities, or also the third velocity in the case of the 3D cases, the temperature. Oh, you can also get the field of the speed of sound in the solution. This is just straightforward. Okay, actually, I think we're going to move on to our next case. So this is essentially the same geometry, but we're going to be approaching the problem a little bit differently. So as you can see in the previous case, it took us quite a long time to compute the solution, especially on this laptop. As I said, once again, it's really not a very powerful computer. So a smarter solution to this problem is to use a very coarse mesh initially, and then to adapt it. So once again, we're going to clear our workspace, and we're going to display. Yeah, so this is just the old solution here at the top, and here at the bottom. Actually, let me just call it right this like this. Hello. Oh, perfect. Sorry, it's here. All right, so this is the mesh we're going to be using for this case. Once again, the geometry is identical. I have sort of made the initial mesh a little bit finer on the bump. The reason for this is actually not much to do with the solver itself. It's just that basically the angle of the shockwave depends on obviously on the angle of the bump. So since we use a numerical method, the finite element method, we have to divide the domain into elements. And so here you can see that the initial element here, the angle at which the element is tilted off the x-axis. Excuse me, that might have not been the best way to put it, but anyway, the angle of this segment basically is not exactly what the tangent to this arc at this point would be. So if we were to compute sort of the analytical solution, we would have to take the tangent here. And obviously, since it's a discretized geometry, the angle at which this segment lies is not the exact angle at which the tangent would lie. But basically, the smaller the segment, the closer the two angles are. So this is a good approximation. But if we took, for example, a very large element like from here to here or something, then you can tell that the angle would be significantly smaller, which would result in a significantly different solution, less physical one. Excuse me. Once again, I do apologize. All right, perfect. So yeah, let's go over the code. So here, once again, it's the same exact story. We define the boundary IDs, we define the reference values, the initial fields. This is all the same as in the previous case, and perhaps we take a little more iterations. The difference is right here. This logical condition checks if the norm of the increment compared to the norm of the solution is small, meaning if this condition is true, that means that the solution isn't really changing that much. So if the solution isn't really changing that much, then we can adapt the mesh where necessary. This is simply that we're saying that we're going to adapt the mesh, I think 8 times because we're starting at 0. Yeah, maybe we can adapt it just 7 times. So yeah, this is just so we don't adapt it infinitely. Just we stop at a certain point. So here the key function is AMR, which stands for Adaptive Mesh Refinement. What this function does is it takes the mesh, obviously, and the solution. And here the 5th argument, weighted pressure jump. This is the argument in general which defines which elements the function needs to divide into smaller elements. So you can go with a few options here. You can simply tell the function directly which elements you want it to refine, or here in this case we give a vector which has the weighted pressure jump, meaning the norm of the pressure gradient in this element weighted by the area of the element. And what this function does, it'll take the vector, it'll calculate its mean, its standard deviation, and it'll adapt all the elements for which this value is greater than, I believe, the mean plus 1.6, the standard deviation. There's a heuristic parameter there. In any case, it'll only adapt the elements which are above a certain value. And after that, we simply plot the mesh. So without further ado, let's just run this. There we go. I'm gonna hide the residuals for a second. It's not really. I'll show them to you after we're done, or after a while. So here, as you can see, the iterations are happening fairly quickly. I'm sure you can already tell that the solution is super inaccurate. The mesh is extremely coarse. This would not be acceptable at all. But that's not our objective right now. Our objective right now is simply to calculate a sort of initial solution and estimate where the shock waves are going to appear. And then we're going to adapt our mesh in the shockwave areas. So as you can already see right here, and after the shockwave is reflected. So yeah, it's gonna take a little while longer. But after this is why we're checking the norm of the increment of the solution against the norm of the solution. after the solution sort of stabilizes, we will adapt the mesh. We don't want to adapt it just willy-nilly. We want to actually wait for the solution to sort of stop changing drastically, and then we're going to adapt it. So yeah, we just have to wait for it to happen. It's going to adapt basically over here along the shock waves, hopefully sometime soon. Yeah, there we go. That was the first iteration. As you can see, here the mesh is a little bit finer. This will become much more visible after several iterations of the adaptation. And when we look at the residuals, you can see a spike in the residuals where the adaptation took place. Obviously, we have some new. Basically, the way the new results are the results on the new mesh are simply interpolated from the old one. So it's very straightforward. Obviously, the residuals are going to spike, and it happened once again. Here we go. Maybe you can see it a little bit better now. Beg your pardon. Oh, well, perfect. So here, I think we can see the shockwave sort of taking form and becoming sharper and sharper, gaining in resolution, essentially. Yeah. Oh, wonderful. This is very. It's very spectacular. It gets me every time. No, but frankly, it's just very useful. It really saves us a lot of computational power. As you can see, we already have a decent solution, and in the previous case, we had to wait a long time. This entire part of the domain in front of the shockwave, it's discretized with an extremely coarse mesh. So you can see here that basically these elements are like, well, they're several times bigger than the elements used in the previous mesh. Yeah, so here you can see it's getting quite fine in the area of the shockwave. And we've achieved a much better solution, frankly, than we did earlier, or we would have earlier after it stopped, after it converged, simply by adapting the mesh only where necessary and not using a globally coarse mesh. Yeah, and I'll show you the residuals. We have 5 adaptations. 5 adaptations took place. So we're going to give it a while longer, and then I'm going to zoom in on this mesh because it's, perfect. Another one. Great. So honestly, this would keep going for a while, but we don't really have that much time, and it's not the point to actually sort of to get a super converged solution. I'm sure you guys get the point. So what I'm going to do next is we're going to stop this. I'm just going to terminate the run. I'm going to close this, and I'm going to display the solution, or the mesh rather. Perfect. So here you can really see the power of adaptation, or mesh refinement. In the shockwave area, as I said, the elements are very fine. Maybe there's a new region where it's finer. Maybe I'll try here. Yeah, anyway, you can see the elements are very small. The mesh is very fine. And then when you move in front of the shockwave, the elements are still huge, which saves us really a whole lot of computational power and computational resources. All right, so I think yeah, this took long enough. So I think I've said everything I wanted to say. I hope this was somewhat informative, and I hope that this explained some stuff about our compressible solver. So now we're going to move on to the Q&A. All right. So if you guys have any questions, please ask them now. Like I said earlier, you can access some sample results, and so you can access the tutorials on our website, QuickerSim.com, or you can simply download the toolbox, the new version. I encourage you to do that, and you can check them out there. Yeah, we can basically we do like I said, we do not need a boundary layer here because this is an this is an inviscid solver. So the boundary layer is generated to resolve turbulence or to model turbulence, depending on your models, obviously. And we simply don't need it since there is no boundary layer for a fluid because it's inviscid. Mesh adaptation. No, mesh adaptation, frankly, I do not know if it's available in the PDE toolbox. The function that I showed you, AMR, Adaptive Mesh Refinement, it's our function. Actually, I wrote it. And it works, unfortunately, as of now, it only works for two-dimensional cases. Hopefully we'll have it for 3D in a future version. But it's our function. It's not available for the PDE toolbox. I'm not really familiar with the PDE toolbox that much, so I'm afraid you're gonna have to see the MATLAB documentation. When does the code refine the mesh? So that's a great question. As I said, basically, the residuals. Well, the residuals are obviously one way to sort of, or one way to identify when to adapt a mesh, and that is an absolutely, that is a fine sort of benchmark for adaptation. But in this case, I think what I personally prefer, and in my experience, what really works a little bit better, is you don't wait for the residuals to drop, since, frankly, you can't really, I mean, the residuals can be a little tricky estimating when a solution is actually converged. But what you can do, and what I've done here, we check for the change of the solution. So what we're saying here is that if the relative change of the solution is under this threshold, then we're going to adapt. So if the solution is changing from iteration to iteration only a small amount, this is we don't really notice this magnitude of change that much. So if the flow is developed enough, then we adapt the mesh, and then we wait for the flow to develop further, and then we adapt again, etc., etc. So I hope that answers that question. Which linear solver is used? So actually, this is a interesting question. So in this case, we just use the MATLAB Direct Solver right here to check which specific solver you can type doc ml divide. This is the MATLAB function. That's the backslash, basically. It's actually a kind of a cool element of the MATLAB help. There's like a block diagram here which shows you the sort of decision process that MATLAB goes through, or this function goes through, to determine which linear solver to use. So I mean, you can look through this on your own. It's a fairly sort of advanced decision process. Why I said this is an interesting question is because actually the method, the formulation that I use here, the least squares finite element method formulation, It's a pretty cool formulation because it leads to symmetric and positive definite systems. And as anyone familiar with numerical mathematics knows, symmetric and positive definite systems can be solved using the conjugate gradient method. You can look it up in MATLAB. It's PCG. Just PCG. Yep. And it's a very efficient iterative solver. We don't use it here because it's really, frankly, for small scale cases, the direct solver is always more viable. Also, there are some fairly complex numerical difficulties with this formulation. In like its primitive form, you wouldn't really get good results, or you wouldn't get fast convergence. You wouldn't get good convergence with the iterative method. You can read about it if anyone is interested in the least squares finite element method. Please contact me. I mean, my email is on the website, and it's. Sorry, this is maybe not the most elegant way to give you my email, but if anyone has any questions about the solver or generally the case, or frankly any other questions, please feel free to hit me up at this email. I'd be happy to talk to you about the least squares finite element method. It's one of my interests. So. All right, let's move on. Is it possible to model 3 geometries like F1 car rear wing for aerodynamics? Yes. We do have a 3D compressible solver, but unfortunately for F1 cars, I mean, you could use this, but frankly, you would need an actual compressible solver, which also includes viscosity, so you can model turbulence. This could be useful for essentially maybe low Reynolds compressible flow, if there's such a thing, or you could use it to estimate some aerodynamic properties like lift and or just lift, etc. Adapt the mesh. Yeah, sorry. Maybe I didn't get too in depth on that. What this function does, it calculates it takes the pressure gradient, it integrates it over the element, I believe, and yeah, I think it integrates it over the element, and then it takes the norm of that integral. So essentially, what it says is how much the pressure changes across the element, hence pressure jump, and it's weighted by the area of the element. So if it weren't weighted by the area of the element, perhaps you would only adapt the elements on the shockwave. It would be sort of too focused on the shockwave. So if you adapt an element several times, then sort of because the area is obviously smaller, then the weight, the area weight will be smaller. So you'll also kind of adapt around it. This is actually this is kind of just like a good practice, and this works in practice better than a non-weighted pressure gradient criterion. I hope that answers that. Turbulence models. So I think once again, this is an invested solver. So this particular solver does not have any turbulence model. But in our incompressible solver, excuse me once again. Oh, excuse me. In our incompressible solver, we have several turbulence models. So you can go on our website and read about it. But we have the KL model. We have some zero equation algebraic models which work perfectly fine for a lot of applications. For our next release, we're working on the Spallert-Almaraz model, which frankly is one of the more commonly used models. It validates extremely well against the experiment. And just in general, expanding our turbulence model base is something that we are working on. We are not an old company, so this code is fairly new. So we're still expanding it. And if you would like to tell us what direction you think we should go in, or what our clients need, then we're going to develop based on our clients' needs, obviously. So you can kind of, if you buy our toolbox, you can kind of have a bit of a vote in which way you'd like the development to go. Yeah, so I think my colleague linked the turbulence models in chat. What is the computational power required for this? By Tushar Goyal. I'm sorry if I mispronounced your last name or your name. Very small. This simulation is, as I said, it's run on a really old laptop. So this is what I just showed here, you can run on anything really. And in general, our incompressible solver, which is sort of the main part of the toolbox, because we have new iterative solvers in the latest release, you can run even big cases on fairly simple or fairly not very powerful machines, so laptops. Is adjoint optimization for flow control available in your solver? No, it is not. But it is something that we will conceivably have in the future. Fun fact: our CEO got his PhD yesterday, actually, and his PhD had to do with adjoint-based optimization. I also have some experience in that field, so it is something that we are considering for future releases that we will conceivably have in the future. Once again, our employees are familiar with the technique. How much difference would RAM and GPUs make to the power of computational for CFD? In general, obviously, GPUs would make a lot of difference, a huge difference, except especially for maybe lattice-Boltzmann methods. I mean, it would depend on the code. In our code, as of yet, it's not really parallelized. That is also something we have planned for the future. RAM makes the biggest difference, I believe, for these sort of small to medium-sized cases. The RAM requirements for our newest release are significantly smaller because, as I mentioned, the iterative solvers, algebraic multigrid. So, just to give you sort of a rough estimate, in our new solver, on our new version, on a computer with like 16 gigabytes RAM, I think we computed some cases with like I want to say like 300,000 nodes, so like over 1 million degrees of freedom. Which maybe you can't calculate an airplane based on this, but it's there are a lot of cases for which this mesh size or mesh resolution is completely sufficient. Is your solver able to do lesser DNS? No, unfortunately, DNS. This is DNS basically. I mean, DNS is you would need a fine mesh. So depending on your computer, frankly. But I mean, DNS, yes. But we don't have as of yet. We do not have large eddy simulation models. Our solver is for all sorts of meshes. We do not have our native mesh generator, but we take advantage of Gmesh. Gmesh is free and available to be downloaded online. It's actually a very, very good mesh tool. It's once again, it's free, and it can mesh 2D and 3D geometries. You can import step files into it, which is great because I mean, I'm sure everyone has some sort of CAD environment that they like to use, and you can simply generate your geometry there and import it to Gmesh. And then you can import after you mesh it in Gmesh, you can import it to our toolbox using this function. Excuse me. Import mesh Gmesh. This is, as you can see, it's very simple. There's no complex coding required. Can I replace any part of the code with my own code? Yes. This is one of the biggest strengths of our toolbox. We can absolutely replace any part of your code, of our code, with your code. Our sort of whole framework is very flexible, and the idea is that we sort of give you building blocks, and we give you some initial ideas how to perform simulations, but it's kind of up to your imagination essentially what you can do with those building blocks. So I think flexibility is one of the biggest strengths of our solver and our code. And I mean, MATLAB in general, it's just it's a high-level, very open, well-documented environment. So a lot of other CFD codes. Excuse me. Oh, I'm really sorry. Other CFD codes have sort of a very high threshold to start using them. And it's kind of, it takes months to learn the basics. Here are sort of one of our initial slogans was that you can perform CFD simulations in 12 lines of code. So it's very flexible, and it's very simple to learn, really. What about conjugate heat transfer? So basically, obviously we have a heat transfer module, and we have you can do it. You can have a flow in a channel in some sort of solid geometry, and you can compute the temperature fields, or the basically heat transfer in the fluid and in the solid simultaneously in conjunction with each other. What is the reason we chose the finite element method? This is it's kind of it's a lie to say it's a personal preference, but we basically our initial development was in the finite element method. But I personally believe that the finite element method has some advantages, or significant advantages, over the finite volume method. I'm sure a lot of you are going to tell me that the finite volume method conserves mass much better. But actually, you can conserve mass just fine in the finite element method if you know what you're doing. Frankly, FEM parallelizes much better, which is something that we're going to do in the future, but in general, it parallelizes better. It has some other advantages. Our developers, I believe, are mostly have experience with the finite element method. Yeah, frankly, this is an open discussion. I'm sure if you go online and read it, or just from experience, or read online about people discussing which one is better, FVM or FEM. It's a very much open question. Is it possible to write an adapter for MPCCI or pre-CIC for coupling? We do not have that. If you would like to write one for yourself, I mean, you're free to do so. Once again, our code is it's very flexible. It's very open. I don't believe we have a lot of plans to maybe go in that direction as of now, but yeah, maybe maybe we can get back to that later. Yeah, so I think we've gone through all the questions, which is perfect because we are 1 hour in. So we are very good on time. Does anyone else have any more questions, maybe? You have spectral method built in. No, we do not. However, I mean, the simple answer is that we do not. But once again, our engineers, our developers, have developed spectral code in the past. I personally did it for my master's thesis, and I know our CEO did it for his PhD. You know, honestly, for industrial applications, I think it's sufficient to use a lower order method and simply maybe adapt the mesh. Now, I really like spectral methods, so I would really like to see higher order methods used in a solver in the future, maybe. But as of now, we only offer the first and second order elements. So in the case of fluid flow, the Taylor hood pair, so second order for velocity and first order for pressure. Is it possible to install Linux MATLAB? Yes. Yeah, there's MATLAB for Linux, for Windows, and for Mac. MATLAB runs and everything. All right, perfect. So if you guys don't have any more questions, thank you for participating. You can find many more tutorials and some other materials on our website. I encourage you all very strongly to download our new release. There's some really exciting and cool stuff in there. And if that's that, then thank you so much. And hopefully I'll see you at one of our future webinars. I think we have one on, no, not Friday, but I'm sure we'll have one next week or in 2 weeks. Since we have some new functionality in our new release, we're going to be talking about it. So I'm excited to show it to you guys, or perhaps for one of my colleagues to show it to you guys. Once again, I apologize for my cold and my sneezing. So thank you all for participating, and I hope to see you in the future. Goodbye.